Let's look at this story problem. Okay, we have a 50-pound speaker. Here's my 50-pound speaker, suspended from the ceiling by 2 support braces. So I have support brace 1 and support brace 2. One of the support braces, I'm going to say support brace 1, makes a 60-degree angle with the ceiling. There's my 60-degree angle. The other makes a 30-degree angle with the ceiling. So I'm going to call that one support brace 2. And I want to solve for the tensions that are on each of these supports. Now, a force or a tension is defined as a push or a pull. The intensity of the push or the pull is the magnitude of the force. So, for example, if I'm looking at vector W, this vector is the vector of gravity. It's gravity pulling this speaker down. The magnitude or the intensity with which it is pulling that speaker down is 50 pounds, because that is the weight that gravity is pulling down on that speaker, 50 pounds. Now, forces or pushes or pulls are always measured in newtons, or if you're in the English system, pounds. So that is also how we get that the magnitude of this weight vector, this gravity vector, is going to be 50 pounds. That's the force acting on it. Now, what I did is, instead of drawing the picture like this, it's more helpful to draw the picture on a coordinate grid. So I put the speaker at the origin right there, and I recreated all my vectors. So this one is tension 1. That's my vector that supports 2 support beam 1. This one is tension 2. That connects to support beam 2. And then here's my weight vector, aka my gravity vector. Now, I know the magnitude of the gravity vector is 50 pounds. I do not know the magnitude of T1 or T2. That's what I'm solving for. However, I do know the angles. Because it makes a 60-degree angle with the ceiling, I can use my parallel lines and do my alternate interior. So if I have that parallel line, these two measurements are the same. So if this is 60, then this is also 60. And then I did the same thing with the 30. Here's my parallel lines. That's 30, so that's also 30. However, I don't want to say this is 60. I want to measure it from in standard position. So that's from the positive x-axis. That would give me 120. So I now have the angle for all of these, and I have the magnitude of one of them. I need to solve for the other 2 magnitudes. So let's start by writing these vectors in component form. W's the easiest, so let's start there. Its component form is easy. 0 in the x direction, negative 50 in the y direction. That's how that vector is moving. It's not moving side to side at all. It is just moving down 50, that negative 50 pounds being pulled down in the y direction. So that's W. Now, T1, we're actually going to go back to using our component form with sines and cosines. We know another way of writing the x component is the magnitude times cosine of theta. And another way of writing the y component is the magnitude times y of theta, times sine of theta. So I'm going to take the magnitude of T1, which I don't know, cosine of 120, and that's going to be my x component. Now I can take the magnitude of T1, sine of 120, and that's going to give me my y component. Now I can do the same thing with tension 2. The magnitude of T2, which is what I'm solving for, cosine of 30, gives me the x component, and the magnitude of T2 times sine of 30 gives me the y component. Now, here's the key to this problem. This speaker is standing still. It is not swinging, it is not swaying, it is not doing anything, it's staying still. Which means I could take my 3 vectors that are impacting this speaker, and if I add them all together, I'm going to get the 0 vector. Because they're all staying, the speaker is staying still, it's not swinging. So if I add them all together, this is how I show it staying still, the 0 vector. So I'm going to put that all together. I'm going to take my W vector plus my T1 vector plus my T2 vector and adding all those together, I should get my 0 vector. So here's what I'm going to do next. I know that when I add vectors, I can just add their components. So let's start by making an equation where we add together all the x components. So the x component of the W vector is 0. The x component of the T1 vector is this. And the x component of the T2 vector is that. It should equal the x component of my 0 vector. So that's what I get when I add all the x components together. Now let's look at what I get when I add all the y components together. The y component of my W vector plus the y component of my T1 vector plus the y component of my T2 vector. Should equal the y component of my 0 vector. Now I can simplify these. Here, if I add 0, I don't really need that 0. And on the y component one, let's add 50 to bring it over. So I get this plus this equals 0. And this plus this equals 50. And you might notice that this is actually a system of equations. Take you back to 1050. I can put these two equations together into one beautiful system. Now, while I'm finishing writing this out, you might be thinking, Mrs. Johnson, why don't you just simplify cosine of 120, cosine of 30, sine of 120, sine of 130, or sine of 30? Because these are all unit circle angles. I could easily simplify these into unit circle angles or unit circle points. However, just because the angles work out to be unit circle angles this time doesn't mean they will always. In fact, I believe there's a question on your homework where these angles are not unit circle angles. And I've seen problems on your final where these angles are not unit circle angles. So I'm not going to simplify them, assuming that you're going to be dealing with more complicated problems. And once it gets more complicated, you don't want to simplify this because then you would get decimals that start to get inaccurate. So I now have this system of equations. I need to solve for T1 and for T2. I'm thinking the easiest way to do this would probably be to solve one of the equations for T1 or T2 and plug that into the second equation. So using our method of substitution. So here's where I want you to come in. I want you to take this equation here, and I want you, step 1, solve this equation for T1. So you're thinking, what do I need to do to get T1 by itself? So pause the video, solve this equation for T1, and then come back to check and see how you did. Let's check your work. So here's what I got when I solved for T1. So step 2, you're going to take this, what you got for T1, and you're going to plug it into the second equation for T1. So I'm going to replace T1 with all of this. Then I should be able to solve this equation for T2. So I would like you to pause the video and try that step on your own. Plug this in for T1, then solve for T2. And by the way, the easiest way to do that is when you plug this in for T1, they're both going to have a T2 in common that you can take out and then just divide by all that stuff to get T2 alone. So pause the video, think through that, try that out on your own, and then come back to check and see how you did. So when I did all of that, here we go, I plugged that in for T1, and I saw that, hey, here's a T2, here's a T2, they have one in common, so I took it out. So when I took a T2 out of this part, this is what I'm left with. And when I took a T2 out of this part, this is what I'm left with. Divide by that whole thing to get T2 by itself. So I divided by it on this side. And this is what I got for T2, which all I just put into my calculator to get that T2 is 25 pounds. So the tension on the support beam 2 is 25 pounds of tension. So my last step is to take this 25 pounds and plug it, go back to my equation for T1, plug 25 in because I now have that answer. Then all I have to do is type all of that into my calculator to get that the tension for support beam 1 is going to be 43.3 pounds. And there we go. So kind of a beast of a problem. I have seen problems like this, usually with easier numbers on your final. So this is definitely one you'll want to practice and make sure you understand. But with that in mind, you are officially done with lesson 7.2. You only have one more lesson for vectors, and then you're done with chapter 7.